Hello, this video is for Stat 310 Handout 12 Part A and will include pages 1 through 6. Okay, let's go ahead and get started. Handout 12 is going to use the Ames housing dataset. That dataset is available in our Google folder for Handout 12. Handout 12 is going to cover multiple linear regression. In Part A, we are going to consider two quantitative predictors. In Part B of this handout, we will consider as many predictors as you would like, or several predictors. So this handout is going to use the Ames housing dataset. The Ames housing dataset, it contains information about homes from Ames, Iowa. And it is a common data set that is used for the teaching and learning of multiple linear regression. I provided a snippet of the data set here in the middle of the screen. We have information about the neighborhood of the home in Ames, Iowa. We have the type of the home, whether or not it was a single family or a townhome. We have the age of the home in years, lot area. We have these overall quality and overall condition variables. If these values are low, then they are of low quality or of poor condition. The maximum value that these can obtain are 10, and that would mean that it is a high quality home. So they have really nice cabinetry or very nice tile, things like that. Also, the maximum value for condition is 10, and that would be a home that's in very good condition. These two measurements here are somewhat subjective. The agent or the real estate agent would have to decide what those are. We have the square foot of the home. We have baths, bedrooms, fireplace, whether or not the home has a fireplace. And then at the end over there on the right, I have my response variable, which is just the sale price of the home when they sold it. So model number 1, we are going to consider a simple linear regression model. And this model is just going to have square foot in it. So this is going to be akin to what we did in handout number 10 with just one predictor variable. A simple linear regression model. And I fit this just so we can kind of have a baseline from starting from. So I'm not going to cover all of the elements here because we did that in handout 10. The R squared I will touch on here. That is 54%. Again, that can be multiplied by 100 and expressed as a percentage. And that just indicates that 54% of the variation in price can be explained using this model. And this model includes square foot as a predictor. The other is the RMSE value here. The RMSE value here is about $54,000. And that will just be the average amount of error when I'm predicting the selling price with this model. Top of page 3 includes more information about the simple linear regression model. Let's look at the bottom of page 3, the consideration of additional predictors. So a multiple linear regression model allows for more than one predictor to be used when making predictions for sale price. The model that included square foot had an R squared of 54%. So if this bar here represents 100%, 54% of that can be explained using our model that included square foot. 46% of the variation in sale price remains unexplained. A multiple linear regression model, in the addition of additional predictors, is going to try to reduce this unexplained variation. So model number 2. Model number 2 is going to have square foot in it, like I had up above, but it's also going to consider a term for age here. So I'm just adding another variable or another predictor. It should be noted that both of these are quantitative in nature. So square foot and age or number values up here. If we go back up here and look at our data, square foot is a number or quantitative, and so is age. We fit this model in JUMP much of the same way that we did a simple linear regression model. We just would put square foot and age in the construct model effects box. So let me go over to JUMP and just do that for you. So here's the Ames data. It has a lot of homes in it, about 1,500 homes. Several variables. And again, we're going to use sale price. That's my response. I'm going to use square foot and also age here. So my predictor variables are age and square foot. My response variable is sale price. So to fit this model, I'm going to select Analyze, Fit Model. I'm going to put sale price here in the Y box. And I will put square foot and age in the Construct Model Effects box here. Go ahead and hit Run. The summary of fit, analysis of variance, and parameter estimate output is given to me by JUMP here. One thing that I will note that is missing is that scatter plot, and I'll talk more about that in a minute. So how about model number 2? Well, if we look at the analysis of variance part, we continue to see that that price can be predicted using square foot and or age. So that p-value is less than 0.05 there. My summary of fit, my r-squared before, when I just had square foot in the model, was 54%. It now jumps up to 69%. Excuse me. My root mean square error dropped down to $44,000. It was about $54,000 before. So including the home's age does have a positive impact on my ability to understand sale price. And that makes sense. A home that's brand new should bring more than a home that is, say, 40 years old or something. So let's talk a little bit about the parameters underneath the parameter estimates. So we have 2 predictor variables and 1 response variable. So I actually am trying to look at the relationship between 3 variables at once. What that means is that I'm in a 3-dimensional space. I made this graph here in JUMP. I can show you how to make a 3D plot quick in JUMP. Let's go back over to our data. Select Graph, Scatter Plot 3D. I want to put my predictors in there, in the Y box. And I want to put my response in the Y box. So I want square foot and age in there, and I also want sale price. Takes a little bit to get this plot in a decent form. And you can just kind of move the plot around. So here, if I change it, so here is looking at just kind of the effect of square foot here. So age is going back into my screen, so I'm kind of ignoring age now. And the trend that I can see is that as square foot gets larger, the price goes up. So when I constructed this graph, I put square foot first, age next, and I put my response last. In doing that, it's going to set sale price here on the y-axis for me. It's not that big a deal if you don't do it in that order. Just down here in the bottom, you can switch that around. I need to turn this graph if I want to understand the effect of age. So now here I'm looking straight at age, and I can see that the older the home is here, then the price tends to go down. So the trend here looks like it's down. The other thing that I kind of see when I'm looking at this is some potential curvature here. And that'll appear in our residual plot when we look at the residuals in Part B of this handout. Okay, so that's how to make a 3D plot. So what does the beta 0 represent here? Well, the beta 0 is going to be the intercept. And that's going to be in that three-dimensional space, where does my, I guess it's not a line anymore, but where does my surface cross the y-intercept? And this is saying that it's not at 0. This test here is testing 0, and it's saying that the surface that I'm fitting does not go through the y-intercept. The beta 1 here would be the coefficient that's attached to square foot. If we go back up and look at my model that I specified, beta 1 here is the coefficient for square foot. So what the second p-value is testing is whether or not the slope in the square foot direction here is different than 0. And it is. Again, the p-value is less than 0.05. So that tells me that square foot is useful in predicting sale price. The beta 2, which is attached to age, is looking at the slope in the age direction here. Okay, so the other slope of this three-dimensional plane. That is also significant. That p-value is less than 0.05, so that tells me that age also has an impact on the sale price. So when I look at tests 2 and 3 together, I know that both square foot and age will have an impact on the selling price of a home. Here's the interpretation of those coefficients. The y-intercept is going to be at about 65,000. That's going to be the price of a home if it has 0 square foot and 0 age. You might be able to think of that as maybe the lot price, because a home of 0 square foot and 0 age is not really a home. The square foot coefficient there is 103. That's just going to be the expected increase in price per square foot. This is positive, so that's going to be an increase. The negative 1042 is the coefficient for age, and that is negative, so that's going to be an expected decrease in price due to a home being 1 year older. Maybe bold those just so we differentiate those, because one is positive and one is negative. Now, when we're looking at the effect of age, I have to hold the square foot constant. In other words, the two homes got to have the same square footage, and one being 1 year older than the other. This would be the amount of decrease in that situation. Or if I want to look at the amount of increase for square foot, I got to have two homes that are the same age. So we say that we must hold age constant when we're trying to interpret the effect of square foot. I communicated that in the following tables here. So on page 6, we can see that this first home has square foot 1750, the other has 1751. So I'm giving home 2 just 1 additional square foot. The age is the same, and I can see the math here. So just plugging these values into the equation, that the expected selling price for home 2 is increased by $103. When I'm looking at the effect of age, I want to hold the square foot constant. So those got to be set to some particular value. Doesn't matter what they are. They just need to be the same. Home number 2 is 1 year older than home number 1. So there's going to be a decrease in that expected selling price by about $1,000. So the regression model here certainly helped in taking away some of that unexplained variation. When I used square foot, the R squared was 54%. When I used square foot and age, the R squared was 69%. So by including age, I'm encompassing or getting 15% of that unexplained variation. Before, the unexplained variation was 46, now it's down to 31. It's being reduced because I'm using more predictors in my model. Well, that begs the question, I could probably use something like the number of baths or the number of bedrooms, etc., to continue to reduce this unexplained variation. So the natural extension here is to not just include 2 quantitative predictors, but to include as many as needed. Okay, bottom of page 6 here. Final comments. The regression model that includes both square foot and age does a better job. It has a higher R squared and a smaller root mean square error. Before we do any predictions with this model, we should check the model assumptions. Also, JUMP does not provide this for multiple linear regression, but you should make a plot of the predicted selling price against the actual selling price. That should fall on a nice straight line, on the y equal x line. If they fall on the y equal x line, that means that my predictions are close to the actual selling price. If that's not the case, then that'll indicate where your model is doing poorly. So I typically create that plot just so I can see whether or not my model is doing a good job at predicting. Okay, that does it then for Handout 12 Part A. Thank you.